We left off Current Meter Project Part 1 with the question of how do we prevent our resistors from burning up and releasing that magic smoke that makes all electronic things work. This is Current Meter Project Part 2, and we're going to explore how to modify our circuit to do that. You got two options for a solution. You can either use resistors that are rated for higher power, like a 1/2 watt resistor for branch 3, or 1 watt resistors, but they're big, they're bulky, and they're probably more expensive. Another option is divide up the current. Instead of all 199 milliamps or 99 milliamps going down that same pathway through the resistors, split up the current. In other words, use some parallel branches. That's why I like this project. It's a good review of both series and parallel. So let's do the third branch first. We need 50 ohms total resistance, but if we put a couple of resistors in parallel, we can split up the current. So here I've erased the series resistors and replaced them with a parallel network. And again, I still need 50 ohms of resistance. So what two values of resistors should I use? So let me show you a way to calculate that. If you know you need 50 ohms, I know that's how much resistance. If I take the reciprocal of that, that will tell me how much conductance I need. And conductance is the opposite of resistance. It's how easy it is for current to flow through a material. So it tells me I need 20 millisiemens. They're measured in Siemens. It used to be called mhos. The reciprocal of ohms was mhos. But now they use the unit Siemens. So if I take 20 Siemens, I could just divide that in half, 10 millisiemens apiece. So what value of resistors would that be? Well, if I take that 10 millisiemens, take its reciprocal, it tells me I need a value of 100. A 100 ohm resistor would give me 10 millisiemens of conductance. And so if I put two 100 ohm resistors in parallel, the result is going to be 50 ohms of resistance. And you can check the math for yourself. Remember the formula for resistance in parallel, 1 over resistor 1 plus 1 over resistor 2. So in this case it would be 1 over 100 plus 1 over 100. Well, that should look familiar because the 1 over 100 is just what I did for conductance. And if we do that on the calculator, I could take 100, take its reciprocal, add 100, well, the reciprocal of 100 again. That gives me 20 millisiemens of conductance, taking the reciprocal of that, and that gives me my total of 50 ohms of resistance. Now for the branch number 4, I can do the same thing, except if I only use two branches, how much current would I still have going through? 199 milliamps, and divide it in half, I would have 99.5 milliamps going through. If I used 199 milliamps and divided it into two branches, I'd still have in each branch 99.5 milliamps going in each branch. Times 5 volts, that's still going to be almost half a watt, 497.5 milliwatts. My resistors are only rated for 1/4 of a watt, so they still couldn't handle it. What if I used 4 branches instead? If we did 199 milliamps divided by 4 branches, each branch would only have 49.75 milliamps, under 50 milliamps. If we times that by the 5 volts, then we are 248.75 milliwatts. Well, my 1/4 watt resistors are rated to handle up to 250 milliwatts, so they should be able to handle it. They'll be close, but they should handle it. So if each branch is taking just under 50 milliamps, 49.75 milliamps each, then that would work. So what values of resistors do I use to get what I need? Again, before I had a 25 ohm resistor. So if I have 25 ohms of resistance and take its reciprocal, it means I have 40 millisiemens of conductance. So let's divide that into fourths. Again, 10 millisiemens apiece. If I take the reciprocal of 10 millisiemens, 100 ohms. So again, I need 100 ohm resistors for each of those. I haven't shown the branch currents for the third branch, the parallel network there of 200 ohm resistors, but you should be able to use Ohm's law to calculate that. And again, this also illustrates Kirchhoff's current law, that however much current goes into a node has to come out. As an example of Kirchhoff's current law, 99 milliamps of current are going in to this node, so 99 milliamps of current have to come out. 199 milliamps of current can go in this node, so 199 milliamps of current have to come out. It also demonstrates Kirchhoff's voltage laws as we add the different voltage drops up to each on these series resistors to get the total. So I really like this project. It's a good review of Ohm's law, Watt's law, Kirchhoff's voltage law, Kirchhoff's current law, series and parallel networks. So here's all my calculations for my schematic. Now let's translate that into putting it in a layout on a breadboard. Watch Current Meter Project Part 3 and you'll see how to take the schematic and put it as a layout on a breadboard.